Hello friend, my name is S.N. Patil. In this video lecture, we will discuss Cayley-Hamilton theorem. Cayley-Hamilton theorem states that every non-zero square matrix satisfies its own characteristic equation. If determinant A minus lambda I is equal to 0 is the characteristic equation of the square matrix A and A having the order n by n, that is the square matrix and order is n, then there is a nth degree polynomial is exists. When we simplify this determinant, then we get the nth degree polynomial. Okay, then Cayley-Hamilton theorem says A satisfy means non-zero square matrix satisfy the characteristic equation. That is, instead of lambda, we substitute the a here. That is a naught a raised to n plus a1 a raised to n minus 1 plus dot dot plus a suffix n minus 1 a plus a n I is equal to 0. Okay. Now, using this equation 2 means using this Cayley-Hamilton theorem, we can find the A inverse. How? By multiplied equation 2 A inverse throughout. Okay. Then we get a naught a raised to n minus 1 plus a1 a raised to n minus 1 and this minus 1, that is a raised to n minus 2 plus dot dot plus a suffix n minus 1. Now here a and this A inverse, that is identity matrix A into A inverse plus a suffix n into A inverse is equal to 0, I into A inverse. Okay. Now put this term in a right hand side. So total throughout term is negative and the simply a suffix n A inverse is remaining and we want the A inverse. So the coefficient is divide to the right hand side. That is the simplified term is A inverse is equal to the coefficient is divide. Okay, and we putting all this term in a right hand side. Every term is negative, we take minus sign is common and the remaining term is a naught a raised to n minus 1 plus a1 a raised to n minus 2 plus dot 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 plus a suffix n minus 1 into identity matrix. In this way, using Cayley-Hamilton theorem, we can find A inverse. Okay, let us discuss the numerical example on Cayley-Hamilton theorem. Now the question is verify Cayley-Hamilton theorem. Verify Cayley-Hamilton theorem. Hamilton theorem. Okay, for the following matrix and find A inverse. Okay, we have the matrix A is equal to 1, 2, minus 3, 4. So here before proceed this, we discuss the flow chart of the verification of Cayley-Hamilton theorem. So A is given in a problem. So first of all, we consider the characteristic equation. Okay, simplify this, then we get the 2 degree polynomial because the order of A is 2. Okay, here we get the 2 degree polynomial. Then by Cayley-Hamilton theorem, put lambda is equal to A. Okay, in this way, the Cayley-Hamilton theorem is verified here. Here for A, we put the given matrix. Okay, and the equation is satisfied. And the question for A inverse, then we multiply this term by A inverse and simplify, we get the A inverse. Okay. So first of all, we consider here characteristic equation. Now consider characteristic equation. Characteristic equation is determinant A minus lambda I is equal to 0. That is determinant. See, this is A, 1, 2, minus 3, 4, minus lambda time. So here if order of A is 2 by 2, then we write here 2 by 2 identity matrix 1, 0, 0, 1. is equal to 0. Now simplify. So 1 minus the lambda is multiplied here. Sorry, here 1. 1 minus lambda, 2 minus 0, that is 2, minus 3, minus 3, and this 0, that is minus 3, 4 minus lambda is equal to 0. Okay, so here instead of this solving determinant, I am putting the formula lambda square minus s1 lambda plus determinant is equal to 0. Okay, where s1 is equal to, say, equation 1, equation 2, where s1 is a trace, means sum of the diagonal element 1 plus 4 is equal to 5. Now the determinant is 4 and minus 6 and minus 9, that is plus 6 is equal to 4 plus 6 is equal to 10. Substitute in equation 2. Equation 2 becomes lambda square minus 5 times lambda plus determinant is equal to 0. Okay, say equation number 3. Now by Cayley-Hamilton theorem, Cayley-Hamilton theorem, what? Every square matrix satisfies its own characteristic equation. That is, instead of lambda, substitute the a square minus 5 times a plus 10 into identity matrix. Right here identity matrix. Then this addition is formed. Otherwise, no. A is equal to 0. Say equation number 4. Now let us verify the Cayley-Hamilton theorem. It required the a square, a, and identity matrix. We know the identity matrix 2 by 2. We have the a. Now we calculate here a square simply because we have the a and we know the identity matrix of order 2 by 2. So a square is obtained by a into a is equal to 1, 2, minus 3, 4. 1, 2, minus 3, 4. Now here first row is multiplied to the first column is equal to first row multiplied to the column 1 into 1, 1, minus 2 into minus 3 minus 6. Okay, first row multiplied to the column, that is 2, and 2 into 4, 8 plus 8. Now second row multiplied to the column minus 3 into 1 minus 3, 4 into minus 3 minus 12. Second row multiplied to the second column, that is minus 6 and plus 16. Okay, so we get this is minus 5, now this is 10, minus 15 and 10. Okay, now consider the left hand side of equation 4. Consider now verification of the Cayley-Hamilton theorem. A square minus 5 times a plus 10 times identity matrix is equal to, now we just calculate a square as a minus 5, 10, minus 15, 10. This is a square minus 5 into given matrix 1, 2, minus 3, 4. Okay, plus 10 times identity matrix is equal to, now we simplify, minus 5, 10, minus 15, 10, 5 is multiplied. Here I am just multiplied 5, not a minus 5, to keep minus sign as it is. 5, 10, minus 15 and 20. Here multiplied by 10, 10, 0, 0, 10. Okay, now is equal to, now here minus 5 and this minus 5 is minus. Okay, that is minus 10 and this plus 10, we get 0. Now second, plus 10 and here this minus sign multiplied here minus 10 and this 0, plus 10 minus 10, 0. Now plus 15 here, sorry, this is minus 15 and minus minus plus 15, that is 0. Plus 10, okay, a minus 20 plus 10 means plus 10 plus 10 plus 20 and minus 20, that is 0. Okay, so we get the 0, that is a square minus 5 times a plus 10 times identity matrix is equal to 0. That is the null matrix. Okay, hence Cayley-Hamilton theorem is verified. Hence Cayley-Hamilton theorem is verified. Theorem is verified. Okay, now let us find the A inverse. So for A inverse, we multiplied equation 4. Now find A inverse. Multiplied equation 4 by A inverse. Equation 4 implies A inverse is multiplied throughout, that is A square minus 5 times A plus 10 times identity matrix is equal to 0. So we multiplied here A inverse. Okay. Now simplify A inverse into A raised to 2. Base is same, addition of power. Okay. That is minus 1 plus 2. That is 1. That is simply A. Now here A inverse into A. That is identity matrix plus 10 into A inverse means A inverse into identity matrix is A inverse, that is 10 into A inverse is equal to 0. Now keep this 10 inverse here and remaining term put in right hand side, that is plus 5 times identity matrix minus, it become minus A, that is A inverse is equal to 1 upon 10 5 times identity matrix minus A. Okay, let us put the value 1 upon 10 5 into identity matrix minus A. A is 1 to 1 to minus 3 4. Okay, is equal to 1 upon 10. Now 5 is multiplied here, 5 0 0 5 minus 1 to minus 3 4 is equal to 1 by 10. Now simplify 5 minus 1, that is 4, 0 minus 2 minus 2. Okay, now 0 and minus minus plus 3, 5 minus 4, that is 1. Okay, so A inverse is equal to 1 upon 10 4 minus 2 3 1. Okay, in this way we can find the A inverse by Cayley-Hamilton theorem also. Okay, thank you.